Look, I'm Walter Jehne. I'm a soil microbiologist. Spent about 15 years with CSIRO, our Australian premier government research organisations, very much looking at the microbiology of diseases, microbiology of nutrition, soil microbiology, and then how do we actually regenerate degraded landscapes. I was working in China with the Chinese Academia Sinica in 1984 for a while, looking at their agriculture, but then joined the Australian government, looking at innovation, commercialisation, actually at a very senior level with the ministers and stuff. How do we actually, then commercialise some of this science rather than just do it as a, academic scientific thing. Retired about 12 years ago, formed this little NGO called Healthy Soils Australia, and that's a network of about 1,000 very innovative farmers, scientists, activists from all around, all different sectors. And like you, basically that's a network of really stunning breakthrough strategies. And yeah, for the last 12 years I've been working in that context, both in politics, but mostly with farmers on the ground. We'll talk a bit more about some of the things that we're doing. So, okay, and here I am today. And yeah, when I was younger, 420 million years ago, there was ocean and there was rock. There was no life on land, okay? And basically there'd been life in the oceans in terms of microbial and eukaryotic cells starting from 3.8 billion years ago. But basically by 600 million years ago, the life in the oceans, which had proliferated with the Cambrian, with eukaryotic and multicellular organism, was running out of nutrients. And so the nutrients leaching from that rock became the limiting factor. In 420 million years, something really special happened, because it was a fungus that grew from the slime of that estuarine edge and grew up onto that rock to solubilize nutrients. And it was a bit of a mongrel activity because it wasn't in the rule book, was it? But basically this fungus grew on the rock and started solubilizing nutrients. But fungi, we know now from the recent work, are just like us. They're heterotrophs. Genetically, actually the higher fungi are closer to us, animals, than any other life form. And basically they can't fix carbon by themselves. So these fungi got smart and they sort of said, I've got to go back into the slime and I've got to pick up a mate. And they picked up this blue-green algae who can photosynthesize carbon. And so this fungus formed a symbiosis, cooperative, synergistic symbiosis between the fungus and this blue-green algae. And they basically then went back onto the land to solubilize. So now they had the solubilization capacity. They also had the carbon fixation capacity. And of course, those symbioses of fungi and algae we call lichens. And they're all over us today. The whole of Vermont, since glaciation, was created by lichens dissolving rocks. And they're still here now. They're dissolving all your rocks, your logs, your concrete, your railway lines. And, those lichens are going to turn our industrial civilization back to soil. Okay, but we don't have to wait for that. We can actually use those lichens. But those lichens did something special then, because it's as those lichens went AWOL and went across the rock to grow independently, and basically as they died, they left behind organic detritus. Just from there's the thing. And fungi are made out of glucosamine. It's like chitin, it's like insect exoskeletons, so their cell walls are glucosamine. And when that glucosamine breaks down, it forms glomalin. And of course, that's exactly what Chris was telling us. Okay, here's this glomalin. And so that was the first organic matter that then was in this rock detritus. Here's some glomalin, organic detritus. And of course, with that, Mother Nature, that lady, she then sort of said, look, here is pedogenesis. Hello, greetings. Here's pedogenesis. Here is the formation of soils. And for the first time, we had soils forming. And of course, the power of this glomalin, the power of the organic matter is amazing, because 1 gram of extra carbon in our soils can then hold up to 8 grams of extra water. 1 gram of extra carbon in our soils because of the carbon matrix it forms has massive surface area with massive negative charges on it, and then massively increases the cation exchange capacity, the capacity of that soil to hold nutrients in forms that are then available to plants. In the rock phase, 99% of minerals were unavailable. They were locked up in mineral oxides and mineral forms. But now we had nutrients that were available in cation exchangeable form. They were held there on that organic matter. They weren't being leached. They were there for plant growth. 1 gram of carbon in that soil created then the aeration in that soil that allowed its roots to proliferate progressively into that soil and increase the volume of soil that, that living matter could that plant matter could, or that lichen could exploit. And so very, very rapidly, we had evolution of the whole biosystem, from those lichens to liverworts to mosses to ferns to cycads to gymnosperms to angiosperms. And then, of course, the grasses came along about 50, 60 million years ago. But so the whole evolution of life forms was driven by petagenesis, by that simple process of Mother Nature or that lichen going AWOL and sort of building up those soils. And the same as we then built that whole biosystem, that whole terrestrial biodiversity, we built an extended green living matter right across the 13.9 billion hectares of land on this planet. And so then in no time at all in the Carboniferous and the Permian, we had then vegetation, forests covering the whole land surface. And so that simple process of that lichen, that glomalin, that petagenesis then created the terrestrial biosystem. And why I say this is, Mother Nature had a hard time getting started. She had pretty sort of restrictive conditions. So we don't have to worry about complaining, hey, we've got limited resources as well. Because it's all about regenerating the Earth's soil carbon sponge. Handful by handful, organic matter compost into that school garden, and every square meter, every handful, every square meter, every acre, every continent of land that we can bring that carbon sponge back into, then we're getting this massive dividend in water and nutrient availability and rootability and the volume of soil and the resilience and the productivity that it delivers. Okay, so we're saying here is in a sense how nature solved this problem 420 million years ago, and it's in a sense nothing's changed. Well, we're all part of nature, and that's exactly the same tool and then the actualization, the agency that we have to take that same process, to take petagenesis and rebuild our soils. So no matter how tough it is or how small we are, that lichen was also small. Hey, look what it did, we can do it as well. And of course, the other thing that we then come to respect and really appreciate, that soil and that soil forming process is a crucible of life. Okay? That soil forming process is really where the whole terrestrial biosystem comes from. We're just simply, omnivores that so then came from the herbivores that were living on recycling nutrients in that forest that evolved from that petagenesis processes. So we can see the whole challenge that we've got, whether it's climate change, building soil, or restoring nutritional integrity of our food and our preventative health, all coming down to this very simple petagenesis solution, the tool that Mother Nature gave us. So really that's the encompassing message for the 3 days, rebuilding that soil carbon sponge. And actually we're going to go through how to do it specifically, what the process is involved. But this morning then I wanted to talk particularly because that sponge not only created our biosystem, but it also created our hydrology. Because that's why we use the word sponge, right? Because that carbon now was able to hold water on the land. And it was that sponge that hydrology that created our climate. Okay, here's a question because it's interactive. What percentage of the global heat dynamics on the blue planet is governed by CO2? What percentage of the global heat dynamics on the blue planet is governed by CO2? Have a guess.
27.
27, right. One.
1 out of 5.
Yeah.
1/5.
1 or 20%.
20%.
0.03%. Yeah, that's the concentration of carbon dioxide. Well, look, it's about 4% of the heat dynamics, right? 95% of the heat dynamics of the blue planet, obviously that's the giveaway, is governed by water. And it was a sponge and the capacity to hold water that was fundamental in buffering and regulating the heat dynamics of this planet. It's why we have ice ages, as 420 million years ago, we created the sponge, that hydrology, that buffering, that we've been able to, nature was progressively able to cool the planet, despite the sun getting ever hotter. The solar constant, the sun's a nuclear reactor, it's always getting hotter. And yet the Earth has been getting cooler because of these hydrological dynamics. And now let's talk about climate change, and really, but that was an intro into that climate change story, because what it's telling us that, again, we want to go back to what nature did, right? How did nature regulate the heat dynamics of this planet? We've got a problem, but we don't want to just get caught in the problem. As Peter said, we've got to look at smart solutions, and just as with petagenesis, can we go back to what nature did with a heating planet or how to buffer climates, and can we learn from that? So now let's just step back now into 50 years ago, like 1958 initially, Charles Keeling in Hawaii for the first time sort of then came, this is nice, isn't it? Okay, and then this is CO2, and this is of course time, and Charles Keeling gave us this beautiful graph. Let me draw it. And basically there was CO2, right? And CO2 was going up, and it had started at the 280 parts per million, and it was growing at that stage about 1.3 parts per million per annum. It's now growing at 3 parts per million per annum, so watch out. But basically, yes, CO2 was going up. And that data was there 50 years ago, Charles Keeling from Hawaii, right? 1958, but by the early 60s, mid-60s, it was substantial. So much so that your President Jimmy Carter in 1978 sort of said, look, we've got to take this thing seriously. I mean, Jimmy was a pretty serious sort of guy and genuine guy. And he said, we've got to take this seriously. And he gave a commission to Los Alamos and the Scripps Oceanographic Institute at San Diego to say, look, hey, what's the consequence? What's the consequence of this CO2 rise in terms of global warming, but particular to America, where are the consequences? And of course, these scientists then sort of said, right, okay, our brief is to look at what is the consequence of this rise in CO2 to global warming, and they narrowly defined it, but they defined it only in the context of CO2. And they sort of came up with an analysis, totally right, that yes, this rise in a doubling of CO2 will increase the temperature through the enhanced greenhouse effect by about 0.3 degrees centigrade. Okay, and it was therefore from a doubling of CO2, 0.3 degrees centigrade. Okay, so if we draw there, okay, this is Manabe and Weatherald, about 1997. I mean, they were doing the work and thing, and basically the graph was basically, okay, here's temperature, here's CO2, here's 100%, okay, here's 200%, and basically it was a graph, like that basically went that way, but it hit a plateau. The difference was about 0.3 degrees centigrade, right? And so came back to, and well, actually they reported not to Jimmy Carter because he'd left office. They reported to Reagan, report to the president 2000. I've got a copy. I'm sure you've all got a copy at home too. And basically sort of said, look, yeah, that's the story. And yeah, it's benign. And there's a CO2 plateau. And obviously what happens is that, see, once you get more CO2 in there, there's enough molecules and the re-radiation of the energy from the Earth isn't going to sort of, I mean, all of it's being absorbed, so we're getting this plateau effect. But of course, this was nowhere near what we were even recording then as a abnormal temperature rise. And so basically the scientists sort of took on board to say, well, look, this doesn't explain what we're seeing in reality. And in a sense, what's in reality is that there's also a water vapor greenhouse effect. In fact, water vapor represents the most dominant greenhouse gas. You know, water vapor represents 60 to 70% of the greenhouse gas effect. CO2 is about 20%. So when they included the water vapor effect, then they were able to say, yeah, look, I can get the 0.8 degrees warming, and it, in a sense, keeps going up a little bit because as the temperature rises, there's a positive feedback. The air holds more water vapor. And so in a sense, in this story, why I'm saying this is that they incorporated this water vapor greenhouse effect as a secondary feedback on the CO2 effect because they needed to meet their obligations. Carter had asked, you know, what's the effect of CO2? So they said there's a direct effect of 0.3 plus there's this water vapor effect. And that's all solid science, but we've actually sort of made a big mistake because we've assumed this water vapor effect is a condition of the CO2 rising. But of course we all know that no, water vapor is completely independent of CO2. You know, whether it rains and what evaporates depends on trees and transpiration and surface water and our sponge. Okay, so all I'm just saying here, or trying to illustrate with the science, that we're getting straight away what Peter said, look, here are academic assumptions and constraints and model restraints. And in fact, it's not the CO2 that's the actual big problem. It's actually the water vapor that's actually driving most of the enhanced greenhouse effect. You know, the component effect of water vapor is much bigger than CO2. And that's the whole point, you see. They can model the CO2 greenhouse quite easily, but the water vapor effect was just too complex in time and space, you know, because it's just variable from time of day, from wherever you are, and every aspect of landscape management, so it was just far too complex to model. They also made the assumption because water vapor is such a dominant driver of that global heat dynamics, 95% vis-a-vis 4%, they made that brave assumptions that we humans could not possibly have altered the hydrological component of the Earth's heat dynamics to influence global warming. So all of climatology, as you know, Glenn has sort of rightly sort of said, it's all there, peer-reviewed, you know, most important scientific papers, there they are. The evidence is absolutely crystal clear, climatology 101, here are the dynamics. But I don't want to get too detailed into, you know, like, I mean, the scientific arguments here, but it comes back to this simple point here that what's happened now is we've been sort of so hooked on this CO2 rise, right? It's now 400, what is it, Glenn, 402, 3, whatever parts per million, right? ppm. And it's going up rapidly.
400 again.
Yeah, no, appreciate it. And it depends seasonally and stuff. But what I'm saying is that, yeah, we were rising. And the point I'm really trying to make is, look, we've, for the last 50 years, have been locked in climate change, CO2, abnormal greenhouse effect, and therefore the whole response and solution has to be, hey, we have to stop emissions of CO2 to try and stop this thing going up. Okay, so the point is that we've been locked into this whole game of global warming is about this CO2 rise. And of course, they forget about Charles Keeling's graph, isn't it? Because what did Charles Keeling's really graph tell us? Because he sort of said every sort of winter we are emitting, and basically every summer and spring we are drawing down carbon. Okay? Because that's what the sawtooth, and that's been going on every year like clockwork, right? So basically, sure, we have got an imbalance between what we're emitting and what we're drawing down each year, but there's our answer, isn't it? Hang on, what has caused this imbalance? This imbalance goes back to 1750. We've only been massively using fossil fuels for the last 50, 60 years since the Second World War, exponentially. I mean, this was basically land management. Okay? And again, it's all documented, Rudderman and stuff like that. Look, for the last 10,000 years, we've been burning forests, clearing forests, oxidizing soil. Hey, we've created 5 billion hectares of man-made desert and wasteland on the 13.9 billion hectares of this planet. UNEP figures. That's over the last 10,000 years. We go to Tibet, we go to Iran, we go to Iraq, we go to Turkey, we go to Greece, we go to Italy, we go to North Africa, and you look through the histories, the anthropology, and basically, hey, these were all forested, green habitats. The Germans went into Tibet, looked at pollen cores in lake sediments, went down 6,000 years, chock-a-block cedar pollen. And you look at Tibet now and it's just, a semi-arid, icy wasteland. Okay, and so our impact on land, through land management on the planet in terms of this capacity of drawdown is enormous. And of course, as we burn this stuff, we're putting all these emissions up, right? And so the answer here is really quite simple, right? We've really got this imbalance between our emissions every year and our capacity, or the capacity of our residual biosystems to pull it back down again. Okay, now this deficit every year is about 10 billion tons of carbon per annum, right? And it's very simple, and this is what we'll come to tomorrow in detail how to, but we've got a simple story. Yeah, well, look, okay, we've got to increase that carbon drawdown, at least that 10. But if we're going to get carbon coming back down again to 200 or 350 parts per million, which some assume is safe, we might have to put down another 10 billion tons of carbon of legacy or heritage emissions, right? Because obviously that'll just keep it stable at 400. Of course we've got to reduce our emission, that's no question at all. No one's saying no, we don't slow down emissions. But we're at a stage now that even if we stopped all fossil fuel use now, hey, this is going to keep on going up. And why? Because 71% of this planet is covered by oceans. 29% covered by land, and as we say, of that 20% roughly now is vegetated, of the total, surface area of the planet. And those oceans contain 38,000 billion tons of carbon dissolved in the oceans. Okay, the land only has 750 billion tons. So 50 times more carbon in the oceans than there is in the land. Okay, and as those oceans warm, those oceans are now absorbing 93% of the extra energy on this planet, so they're warming. As those oceans acidify, as more CO2 goes in and as they warm, those oceans are going to release carbon. Okay, it's a saturated system, it's a buffered system, and therefore as they warm and acidify, they're going to re-equilibrate carbon from the oceans. And so this thing is going to keep on going up, 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 even if we stop fossil fuel use now. Okay, so we're now locked into a CO2 rise, We don't know exactly what level it'll get to when. I'll put money on it will be over 800 parts per million in 50 years' time. But don't be scared, because in a sense, I think that trajectory is now out of our control, and it's being driven by these ocean re-equilibration and the soil oxidation and the tundra oxidation effects. But the point is that it's not going to kill us, but there is something fundamental we have to do, because if we just leave this CO2 and think we're going to stop it through stopping fossil fuels or that whole carbon management, we're cactus, we're history, we're way too late for that, 30, 40 years too late. 10 years ago in Exeter in Britain, there was a major conference, and for the first time it's really forced, like we're talking about, forced reality. And it was looking at dangerous climate feedbacks and extremes. See, because what's happening now is that we've realized that it's not the CO2 that's going to cause the trouble, it's storms, it's Irene, it's Katrina, it's Sandy. It's these hydrological extremes that actually the things that do the damage. And Irene so well, you see, and they're the things that are going to impact. And then it's the aridification and drought. I flew over California, and literally California is cactus. In the next 10 years, this is serious, like does America abort California as 40% of its food production and the home for 120 million people? Because it's aridifying systemically as all the other Mediterranean regions around the world, Southwest Western Australia, the Mediterranean basin are as well. You see? And so it's not the CO2 that's going to do the damage, it's these hydrological extremes. With the aridification, guess what happens? You get wildfires. And last summer, Fort McMurray in Upper Canada, Blaine, okay, I was on the radio yesterday, and they were saying, hey, you got fires in Tennessee. Tennessee was always wet and moist, and what are the fires doing there? California burns every second year. And basically every year, 300 to 400 million hectares around this planet is burning. And of course, that's both massively emitting carbon. We've never accounted for that carbon from fires. They've never been, Keeling would have accounted it, but no nation has to account for their emissions from fires, because that's an act of God or, Mother Nature. But more seriously than the emission, we are also compromising the capacity of those residual biosystems to draw down carbon. Okay, and so in a sense, that little diagram of Keating's from 50 years ago defined the problem. We went off onto this, science of greenhouse warming and temperatures and stuff. That's fair enough. But the real answer was always here, wasn't it? Between, the difference between A and B. Are we going to sort of manage that balance? And if we do, we have to, without any question, increase B 20 billion tons per annum. And you say, is that a big job? And yeah, of course it's a big job, but how big is it? Well, every year, basically, there's about 120 billion tons of carbon that's drawn down by green matter on this planet, right? The biosystem. Half of that is in the oceans, the phytoplankton, and half of this is on land, the residual land, right? 60 billion hectares, 60 billion tons of carbon. So our challenge is almost, can we increase the longevity, extent, and effectiveness of green carbon drawdown by some 20% globally. Globally, yeah.
1/3 if it's all on land.
Sorry?
1/3 more if it's all coming from the land.
But 1/3 if it's from land, 1/3, 20 billion.
And we have much, I think, more capacity to work on the land?
Oh, absolutely, yeah, well that's the other thing, a very good point there, you see, because in a sense, we live on the land, we've stuffed the land. The only other thing that's really powerful, and comes back to Peter's in the thing, you see, it's only on the land that there are carbon sinks that are there in a long-term substantial way, which is the glomalin and the humates that then form the coals and the fossil fuel. Most of the carbon that's fixed in the oceans by phytoplankton is used then in food chains and very rapidly ends up back as CO2. There's some organic detritus, but there's not a real major carbon, organic carbon sink build-up from the oceans. And so we can do, we've got a combination. Yes, of course, we've got to slow down emissions. No question whatsoever, right? But now we've got a question of, can we increase the area of green? Okay, and the answer is yes, we can. We've got 5 billion hectares, which is nearly 30% of, or 40% of wasteland and desert. Now, we can't do all of it, but there's a lot of savanna, grassland, grazing management where we can recolonize, regreen, so we can extend the area because we've wasted so much of it. Can we increase productivities? Yes, we can, because we just talked about 1 gram of carbon is 8 grams of water, is extra carbon, cation exchange capacity, extra nutrition. So can we increase the productivity of biosystems by improving that soil carbon sponge? Yes, we can. But the biggest factor of all, and again, this is so fundamental with hydrology, is when we increase our sponge, we increase the longevity of green growth. And if we say this is basically, if you look at flood peaks, right, of water events. So this is volume, and this is time. And if you have concrete or rock, obviously you get a rain event, and here's your runoff profile, isn't it?
I ground in Vermont.
You're ground in Vermont, yeah, yes, spot on, okay. See, this is beautiful. But if we then build the sponge, we get something quite different. We'll have the same rainfall event, and we'll end up with that. Because the sponge is absorbing that water and then basically slowly releasing it. But the powerful thing that we completely have left, and grew up in the Green Revolution, scientist, lab coat, clipboard, and looking at the plants, and it was always, hey, what are the bigger plants? How do we grow them bigger, faster? So you saw the pot trials, here's the big plants, and look at this big green. Okay, and it's rubbish, because nature didn't grow things faster. Nature grew things for longer. It's a longevity of green growth. And look at this. Basically, if we're saying, okay, we're growing plants here, and this thing can grow for that amount of time, and this one here can grow for that amount of time. Okay? And so it's the tenfold bioproductivity that we can get through longevity of green growth because we have a sponge. Whereas we're lucky to get 20% from all the GMOs, from all the sort of, more, I shouldn't use that word, M-O-R-E-O-N agricultural practices, right? Okay, but the point is that we've all been focused on adding inputs to grow things faster, breeding more vulnerable plants to try and get that extra 10% of yield, when in fact we've got 1,000% yield dividend waiting first just by the sponge and longevity of green growth. So coming to Glenn's point, can we actually draw down this carbon? Again, you've got a guy, he said, yes, we can, because it's all about, can we do that? Longevity of green growth. And then now we're coming to all sorts of, plant health. So there's a whole lot of factors there. Obviously water is an enormously effective trap or a hold of heat, right? The latent heat in water is enormous. So if you've got a sponge and you've got water in that landscape, it's going to buffer temperature extremes enormously. So it might be -5 in the air, but that water in that soil is going to keep it at 3-4 degrees centigrade above freezing, right? And also the fact is, okay, so that's just physically, but then also you've got the plant effect. If those plants have got the water they need, they've got all the nutrient uptake they need. Okay, if you look at their cells, and this is so important, we have a lot of this in our cropping now. So we have a cell, this is in a sense a natural, and this is an industrial crop, right? And you're looking at each cell, and basically the cytoplasm in that natural soil is just so much bigger, right? Okay, so it's like antifreeze. So this is the active organelle, whereas the cytoplasm in this cell is so big, and all this is a water vacuole, right? This is the water vacuole. Okay, and so because it's just such a healthy, vigorous plant with that much turgor pressure, and obviously, you know exactly which plant's going to freeze, don't you? Because these ones with all this water is vulnerable to freezing, whereas this one's sort of driving along with antifreeze effectively in that cytoplasm, right? And no, that's what antifreeze is actually. It's just a solute, right? That doesn't freeze. So do you understand? And yeah, we've got exactly the same effect, but it's not just frost. It's the same thing happens with basically insect attack and vulnerability to viruses and all sorts of stuff. Same thing applies. This is so much more tight, tougher, more rigorous, more turgor, and basically an insect will fly over fields of this stuff to find this stuff, because only that is what's vulnerable and conducive to it. So no, definitely right. Okay, so we've had this sort of very simple, clear evidence from Keeling, but in a sense, I already told you, unfortunately, we've left that 30 years too late. Because as we said, we've got the oceans with this lag effect, and basically CO2 is going to go up enormously because it's going to take hundreds of years of drawing down carbon before we can have any chance of bringing CO2 back down now, right? And so we're in this phase now of CO2 is going to go up, and as we've sort of said from Schellenhuber, or that dangerous climate extreme things, they are intensifying all over the world. As we said, Irene, Sandy, Katrina, aridification, wildfires, these things are intensifying enormously. And so we've got to do something actually especially way outside of this paradigm. See, because up to now we've been talking about our conventional, well, actually not conventional, no one's talking about that, but we've got to now step outside of that paradigm. I mean, we're all saying, yes, we need emission reduction, no question, but we've got to be really realistic and absolutely responsible to say, no, it by itself can't do it. And we've got this bigger drawdown obligation. And I'm just now going to sort of say, look, we've got a bigger problem, because in the next 10 years, unless we do something about these climate extremes, it's those climate extremes, the Irenes, the droughts, the wildfires, that are going to decimate these biosystems so severely that very, very large parts of humanity won't, who are dependent on these biosystems, are going to be really suffering. And we're seeing that now in Syria, because Syria is exactly like California 20 years advanced. Aridification, loss of agriculture, loss of food production, peasants leaving the fertile crescent that they've been farming for 10,000 years, giving up because their soil is just turned to, all the carbon's gone from their soil, no water holding capacity, even with particularly with the reduced rainfall. They've been moving into Damascus, into Aleppo for the last 15 years, and we're seeing the social collapse almost guaranteed. And the point is, we've got 10 years now, and we can't just wait for, taking Adam's point, we can't rely on this, but actually we can't just rely on carbon drawdown. We need the carbon drawdown, we'll come back to that, because we need the sponge. No question, we've got to do this, but that alone isn't going to be enough. Okay, and what we've got to do instead, and this is the topic of today, is we've got to naturally and safely cool this planet. How do we actively cool this planet to, in a sense, offset what this locked-in effect is doing? And how do we then give ourselves that 10, 20 years of viable, green time to build this, or to extend this drawdown capacity? Okay, so is there any, at this point, is there any questions or controversy or details about the point that, look, okay, yes, Adam's point, yes, this is where we're at, and this is what we've been talking about for, 20 years, but we now also have to actually naturally, safely cool the planet.
If you took away the land, would the same cycle be true in the ocean?
Not anywhere near as pronounced. And this is Northern Hemisphere, where Keeling was working. In the Southern Hemisphere, because most of it is ocean rather than land, it's nowhere near as pronounced. It's still there, but nowhere near as pronounced. In the ocean, and if you took away all the land, if you just made the land back to rock, which we are doing successfully, well, concrete, come on. Plastic, okay, but the point is that then it would depend on, sort of phytoplankton cycles. Actually, it's a beautiful discussion here because it's holism. And phytoplankton, it doesn't depend on the seasons, it depends on how much whale excrement is put into the ocean. See, here again is biology driving the whole biosystem, and in a sense we're talking, how do we cool this, how do we get the oceans working? Hey, it's biological, it's that microbiology of that whale gut, and it's that, whale poo that actually drives, we don't know exactly what percentage, but a very significant part of that ocean biodiversity and bioproductivity. So it's amazing. Okay, look, so what we did before we had our break, we looked at the dilemma that we're in, the reality that we're facing, that we've been facing 50 years, the stalemate that we only got to, but also this hard reality that, look, this is going to go up, certainly we've got to do that, but we've got to do more. And it's a little bit now like Albert Einstein told us, you can't solve a problem with the thinking that created it. We've got to step outside the box and we've got to say, hang on a minute, what are the options we got? And of course, my point of view as a humble microbiologist, I sort of go back to, well, what did she do? What did Mother Nature do? Because in a sense, that's really all we've got. And we've already talked about her because we sort of said, look, she solved even a bigger problem. And so, well, how does nature cool this planet? We've already talked about that. 95% of the global heat dynamics is governed by water, water processes. We've excluded those from our models because we've already talked about that. They're too complex, too variable in time and space to model. But that was just an assumption on the part of academics, and it's a convenience because they had to deliver a model to Jimmy Carter's specifications, and they gave it to Ronald Reagan, and of course Ronald sort of said thank you very much and put it in the shelf, and that's where it stayed. But the point is that water does govern 95% of the heat dynamics. And so we've got here a plan.
Sorry, one more thing that went by me. You mentioned the year 1750.
Okay, 1750, right, we just go back in terms of the CO2 increase. We were talking about the Keeling graph, CO2 going up, and we had the zigzag and it was going up. But if you went back, CO2's been going up since 1750, and our point was that fossil fuel use has really only gone exponential since the Second World War, but we were oxidizing massive amounts of carbon from our land through our burning of forests, clearing of forests, cultivation of soil, and desertification of 5 billion hectares of this planet, parts of India and so forth, Rajasthan and stuff like that. And so the point is that, hey, we've been oxidizing, and so the lesson is, hey, we are the agency and we are responsible, and therefore how do we become response-able to fix it, right? So this is what we're about now.
How did you pick 1750? The year 1750?
Oh, okay, we picked 1750 because there's this guy, exactly that, exactly. There's a guy called James Watt, 1760 roughly, and he then perfected the steam engine. And so we were able to transfer now energy from biological energy, horse, people, etc., slaves, they were convenient. But basically we're saying, okay, we don't need biological energy anymore. We can now use fossil fuel, or we can use, mechanical energy through steam. And of course, initially, and you're living in it, wood, right? And the whole of the New England was then effectively deforested for steam for driving engines, right? You previously had water power, and then you basically massively deforested, burned, wasted a lot of it. And of course then basically 100 years ago we went into coal, or a bit over 100 years, 1860, second half of the 19th century. And of course in the 1920s we went into oil, as a major thing. But the point is that it's the land degradation that had driven that carbon increase from 1750. Okay, so look, we've had that paradigm, and now the positive things. How do we naturally, safely cool the planet? And as Einstein said, let's step out and then ask, okay, well, what are the options we've got? What would nature have done? And let's look at it fairly simply. There's an Earth, and every day, 342 watts per square meter of incident solar energy, incident solar radiation, hits on average every square meter of the Earth's surface, right? I mean, obviously it depends on latitude and seasons and stuff, but that's the average. And obviously for a stable climate, you've got 342 watts per square meter having to get re-radiated out. This comes in as incident short wave solar radiation, and it gets radiated as long wave infrared heat. It'll become significant later, but just to set the thing up. Okay, so that's in a sense what a stable climate is. And if we want to cool the climate, let's get to the reality. What do we have to do to cool this rather than get lost in CO2? Because the planet's got another exquisite system. It's got, I'm drawing this thicker than it is, of course. It's got an atmosphere around it. And that atmosphere actually sort of took some of this re-radiated long-wave heat and reflected it back down to the Earth. And that's, in a sense, the natural greenhouse effect. And of course, it was fundamental because that natural greenhouse effect allowed the Earth, the surface, to be 33 degrees centigrade warmer than it would otherwise be. Okay, without the natural greenhouse effect, this planet would be minus 15 degrees centigrade. And of course, at that thing, no life, no water, no nothing. So basically, this natural greenhouse effect was really the critical thing that's enabled life. And that's been there for about 4.2 billion years. The whole planet's about 4.6 billion years old, but water and this natural greenhouse effect has been governing and buffering that climate, that temperature, 30 degrees higher. But what's happened is that we've added to that, and in a sense we've increased the amount of gases in the atmosphere, but actually we've done more than that, and basically now we're getting increased heat getting reflected back down, of 2 there, 3 there. So as a consequence, we're now only emitting 339 watts per square meter. Okay, and that's what global warming is all about. Instead of 342 watts coming in and 342 watts going out, as it was, until 1750 roughly, we are now basically only emitting 339 because we're trapping extra heat, and that's the 3 watts per meter squared heating, greenhouse heating, abnormal greenhouse heating that we're having, right? So that's the problem, right? We are heating this planet, this 3 watts. We don't see 3 watts on the surface. We only see about 1.6 watts on the surface, but another 1.4 watts is actually in the atmosphere. The atmosphere is heating, and so we're not recording that, but it's 3 watts total. It also, though, puts our challenge now in context, because we basically got 342, so we have to really sort of cool this sucker less than 1%. Okay, we've basically got a distortion, 1% extra heating, and now the question is, how do we do it? How did nature do it? And so we really want to now go back to say, okay, well, if they're the dynamics, how do we get 3 watts per square meter extra heat transmission from this planet to actually rebalance the temperature, right? So how do we cool this planet 3 watts per square meter? And of course, what I'm going to go through now is there's about 10 hydrological processes that are involved in this, and they happen sort of sequentially. They all have different heating and cooling effect. This is part of the complexity. Ask questions all through it as we go through this journey. So we're going to take you through 10 stepping stones of how nature naturally cools a planet. And you'll see there immediately, hey, we could intervene here, we could intervene here, or hey, we've stuffed that there, and this is in a sense our cooling options, right? Go through it all, but ask any questions of clarification because, yeah, it is hard science, all peer-reviewed, verified, but, it's a nature works in sophisticated ways. Okay, so the first thing that happens is basically, okay, you've got these things, trees, and basically when there's these trees, and we know these transpire water vapor, don't they? So there's water then gets taken from the soil up through the trees and transpired as gases, water vapor. Okay, that's water vapor going into the air. And for every gram of water, every cubic centimetre of water that gets evaporated, you need 596 calories per gram of heat to turn that from a liquid into a gas. Okay? That's a latent heat vaporization. It's just simple physics. Okay, so basically for trees to transpire, and grass and shrubs and flowers and green stuff to transpire, it needs to transpire water, and then every gram of water it transpires has to take this much heat from the surface and put it back up into the atmosphere. So immediately we've got a cooling effect, isn't it? As we take heat from the surface, transpire it, we're basically transpiring that much. Basically about 80 watts per square meter is what, on the global picture of the 342, is what transpiration globally takes back up into the upper atmosphere, okay? So transpiration naturally cools the Earth's planet, the total transpiration, 80 watts per square meter. It's about 25% of that 342 watts, okay? And so again, straight away, very simple, isn't it? If we can increase transpiration, by 4%, we can cool this place 3 watts per square meter, right? What's wrong with that?
The energy still isn't out of the atmosphere.
Right? No, good. Okay, good. Yes, thank you very much, because this is where we're talking 10 processes, right? Because the energy has now gone up into the atmosphere, and also there's water vapor up in that atmosphere, right? So that's very good. Okay, but so there we are. We have one process, right? So then, and we've been talking about regreening the planet, longevity of green. Remember, longevity green, 1000% potential. So hey, how simple is it to extend the transpiration? Now, the killer thing here, not a killer, it's a bad thing, you're not going to transpire unless you have what? A sponge. Okay? You don't have a sponge, you're not transpiring, right? You're
What?
okay. Sorry.
P-O-N-E?
Sponge. S-P-O-N-G. Okay? Okay, what we've been talking about, here's all this crises and dilemmas, and we're saying that one simple solution is restoring the earth, soil, carbon sponge, right? That's the take-home message. That's the prize you get at the end of this 3 days, the sponge. And the point is that we're making here that this is fantastic, but hey guys, to make this work, we need a sponge. Because every time we're going to come back and say, hey, the punchline, you need a sponge, baby, right? And so that's the message here. Now look, I'm taking up too much board. But now we're going to number 2, which is exactly the question that was just asked. What happens to that water vapor, that heat in the atmosphere? And okay, as that water goes up, it forms haze microdroplets. Okay, and this is in a sense what we're seeing outside the window. We're seeing fog and haze microdroplets, right? And these things are really quite powerful because they're very small. They're about sort of 0.2 of a micron, which is a millionth of a meter. So they're about, 100 billionths of a meter, right? So they're very small microdroplets. And they actually get nucleated. I mean, they form on small nuclei, right? Okay, we'll come back into those nuclei. And so then the question is, the amount of hazes in the air have a profound heating effect. Because it's these haze microdroplets that actually sort of absorb a lot of this incident solar radiation coming from the sun. So there's 342 watts coming in from the sun. And these haze microdroplets, while they're in the liquid state, while they're droplets, will absorb significant part of this. Okay, about up to 60 watts. So whereas we had cooling here, these hazes can actually warm the planet or the atmosphere 60 watts. And we've seen that actually, and I mean that's as a science, and the papers are documented, we've seen this in a thing called global dimming, right? Because we've increased these hazes significantly, because what we've done is we've increased the amount of these nuclei that we're putting up there. Okay, so, okay, let's talk. Yeah, very good, very good. No, very good. Now this is important. This is because these are very important. Okay, let's go back to here. This natural greenhouse effect, as we sort of said, has existed, basically kept the Earth warm and buffered and what have you, existed for 4 billion years plus, right? And it's being driven basically by these hazes, right? So there's a lot of water vapor in this atmosphere, and these hazes are fundamental in driving that. And the formation of hazes depends very much on the production, how many of these haze nuclei are there, because only with nuclei can you form these little microdroplet hazes, right? And so then you look at what are these nuclei, and in a sense in nature there were a whole series of them. You've got the biggest one were algae from the oceans produce a compound dimethyl sulfide. It's just an organic molecule. And so the last 3.5 billion years, thank you. Yeah, good. So for the last 3.5 billion years, these algae, these whale excrements producing blue-green algae, they are producing dimethyl sulfide. And so basically these dimethyl sulfides are very fundamental in putting then the nuclei and then sustaining hazes in the air. And James Lovelock, way back in 1970s, then did a lot of documentation. Here's this whole dimethyl haze formation. They are also, just as dimethyls, they're produced by the terpenes, the pinene, the aerosols that basically get emitted from trees. And your President Jefferson and Monticello basically built that house on top of the plateau because he just sat on his balcony. He was absolutely fascinated by the Smoky Mountains, which again, hazes produced by the terpenes from those forests in Pennsylvania, is it? Virginia, right? Okay. And it was just fascinating. He was actually, he's quite a big mind, and he was really fascinated by this. So basically, these are the things that naturally produce that. And this is all natural. This is these natural greenhouse.
When the H2O gas becomes part of the haze, it's turned into water again. It's turned into a liquid.
Yes. And we're talking about now the liquid phase of this. Okay. What we've also done, and from India and the deserts, the 5 billion hectares, we've also added a massive amounts of dust clay particles, right? And of course they are also operating as haze nuclei, and so now we get a lot more haze nuclei from dust particles. And okay, we've got the whole Sahara producing dust, which then produces hazes, and they go all the way to the Amazon, and it's a massive amount. We've also now added more hazes from our carbon pollution particulates. And so if you go to Beijing in China, you know, you don't go there because it's so smelly and so toxic. But the point is that, you know, like basically they're living in this toxic soup because they put so many particulate carbon nuclei up there, and these hazes are sort of really, you know, health hazard, but they're also massively important in actually absorbing incident solar radiation, and so they're reabsorbing a lot of this. So basically we've had this climate change through massively increasing 300% the hazes that naturally occur and the persistence of these hazes. And so now over India and Southeast Asia, you get these persistent brown pollution hazes, and they're massively effective in warming the planet because they're absorbing this incident solar radiation. So here we are, okay, we've got a cooling effect, but here's another hydrological warming effect.
So doesn't the formation of that droplet actually absorb heat?
Right. Or release the heat.
No, when it,
If it's going from water vapor
yes,
to a droplet?
okay, yes, it will release that latent energy, and this comes back to your question. Sure, as you go from water vapor to form these things will release heat as well. Will release this 596 calories, right? Because it will I mean, depending on, not quite 596, it'll be probably 550, because there will still be temperature in the droplet. But basically, yeah, as water vapor goes into a droplet, it will certainly release this heat. But the higher up it is, a lot of that heat then escapes back out to space. You see, so it's a question of how high that haze and that cloud is. But certainly, it's warming that upper atmosphere, and we, of course, measure that clearly, NASA and stuff with satellites and stuff. You know, so we're getting that warming. So all I'm just saying, here's a hydrological cooling, and we've actually compromised that by cutting the forest back, but we've also compromised the temperature because we're increasing these humid pollutant hazes significantly, and they're both warming. They're also actually significantly aridifying the planet, because while this stuff is in this haze phase, it's not falling out as rain. These are far, far too small to fall out of rain. To form a raindrop, you need about 1 million of these to coalesce to form a raindrop to be removed from the air. Okay, and while they're there in persistent humid hazes, it's an ongoing warming effect. We'll talk about raindrops in a little while, but we're jumping the gun. Okay, so we've got basically, and I put this here because, yeah, we've got the evaporation transpiration effect, and then we've got this haze effect. We've got another fundamental effect, third major effect in hydrology, and again, it's very simple. You know, we say, look, here we've got a forest and there's ground cover, and here we've got India or bare, hard surface, and we've got sort of heat coming onto, so 342 watts minus whatever the hazes have taken away, but that varies. So we've got basically heat coming onto two land surfaces, and again, it has a fundamentally, powerfully different effect because we've got surface albedo, so there's a certain amount of reflection. I mean, the forests reflect about 10%, snow reflects about 90%, oceans again about 10%. But we've got certain albedo effect, but then we've also got this protective ground cover cooling effect. And the answer is, again, here, and especially if you've got a sponge, again, always a sponge, if you've got a sponge, then very rarely do you get temperatures in this soil here going much above 20 degrees centigrade, right? Mostly it's below 20 degrees centigrade because you've got the insulation cover, you've got the albedo, and you've got moisture, and it's keeping it cool. Whereas when you have a bare, exposed, fallowed surface, even zero-till surface, and depending on where you are on the planet's surface, you'll often get to, 50 to 60 degrees centigrade. Okay? And of course, these things are then giving dust micronuclei. Okay, so again, our land management fundamentally alters, and we know that, like when we walk in forested thing, it's all cool underfoot. In summer though, if we walk on bare concrete or asphalt or bare, exposed hot soils, it gets very, very hot. If we just digress for 2 minutes into that, and we have the same thing in Western Australia, and we always sort of fallowed land on the assumption that if we have weeds or anything growing there, they're going to take water away, right? And in Western Australia, we've got the same thing. You were all zero-till fallowing, and then they'd herbicide, Roundup, nuke anything that looked green or looked living or moved, and because it was going to take water away. And we've done the studies too, you see. And where we have these weeds, fleabane, which is just a composite weeds, it's amazing because these things are harvesting water actually from the air. They're actually sort of, condensing in the early morning. They're condensing water on their leaves, and then basically we ended up with situations, let's draw it in red. We had some weeds there, right, occasionally. And here you would end up with pockets of moisture, around those weeds because they're harvesting that. And we'll talk about that a little bit more later because of this water harvesting. And of course that moisture then, as it evaporated, was cooling and exactly that, So it's really interesting. So Liz?
I'm assuming at some point that you're going to get to not just the role of the sponge, but not just the role of the physical sort of carbon sponge, but the role of the microbes and all of this potential for warming, water storage, cooling,
we're going to
all of those types of things.
Yeah, but okay, we will absolutely, but perhaps not as deep as we would go to if we were talking about, because I'm trying to keep it sort of pretty. Yeah. It's complicated enough in a way, but no. Look,
get a little bit sad because you're missing microbes, but that's okay.
Yeah. We're not biased here. We're not biased, Okay.
Not at all.
Okay, but we've set this up. Okay, so there's vast differences in the actual heat. We know that. We can observe that. The kids come back, hey, I can't walk on that field because it's too hot, it's bare and stuff. We know that. And it's actually profoundly important in what we're about to say. Because, okay, we went back to this planet, and we made the point that, we made the point here that, look, the heat that is going out is long-wave re-radiated heat, and that's how we lose heat, right? That's how the planet loses heat. And there's a simple, absolute equation in physics, and, governs the planet, and that's the Stefan-Boltzmann law. And it makes a simple thing that the re-radiation from a black body radiator is proportional, and there's a constant, to the 4th power of the temperature in degrees Kelvin. Now,
say that again?
Yeah. Okay, so the amount of, a black body radiator is like your stove, right? It's your stove or anything that heats up. And anything that heats up loses energy back again, unless it's a nuclear reaction, as a black body radiator, right? And it re-radiates and absorbs heat and then re-radiates infrared, long wave, re-radiates long wave radiation, right? And so the re-radiation is proportional to the 4th power of the temperature. So that means it's temperature times temperature times temperature times temperature. Okay? That's what the 4th power means. And it's enormous, colossal. But it is in degrees Kelvin. Okay, degrees Kelvin is minus 273 degrees, so that the difference we got between 20 and 50 you have to express in degrees Kelvin. But it doesn't matter because it's just such a profound thing. So the more you heat a substance, the more it re-radiates. Okay? Well, if you keep that cool, the less it re-radiates. It's a bit like a stove, right? Have I got the stove on high or have I got the stove on simmer? Okay, now let's talk about the really profound thing here.
And that re-radiation, the units would be watts per meter squared.
Yeah.
Typically, because that's what, there's a factor in there too.
Yeah, yeah. Now let's look at actually, and this is a groundbreaker, let's look at our greenhouse effect. And our green...
Does that to the fourth power mean it's exponential?
Yes, yes, yeah. Very expensive, yeah.
Really increasing
Yeah. And now let's look at the greenhouse effect, right? Now let's look at the greenhouse, the effect, the process. And we've only seen the greenhouse, and we've only been told about the greenhouse effect on the basis of one of the components, the CO2 in the atmosphere. So how many CO2 molecules in the atmosphere to absorb re-radiation, right? Okay, we've basically sort of already had the discussion, but there's also actually water vapor molecules, and there are, like many more water vapor molecules, and actually this represents 60% of the gases. These guys represent 20%, the CO2, and of course we've got our other fellas, the methane, CH4, and CFCs, and other N2O, and they're another 20%, right?
And again, Walter, those are not literal proportions in the atmosphere.
No, they're heat effects. They're the heat effects of these things, right?
Carbon dioxide
Yeah.
is more powerful than water vapor
Okay.
molecule for molecule.
Oh, absolutely. And of course, its molecular weight is 44, whereas water vapor is 18. And so per unit of weight, you've got a lot more water vapor molecules, right? But this is the relative heat absorpting effect. And so we've always been talking about this guy. I mean, that's all that we've been focused on. We've got to reduce these guys that do 20%. We more or less assume we can't do anything about those. And these are carrying along as a pollution thing, we don't know. But they've never talked about this equation, because what governs the greenhouse effect, sure, it's the absorption, but it's also how much re-radiation is coming from the surface. Here is a re-radiation, right? And that is governed by this Stoffen-Boltzmann equation. Okay, and what if we basically turn down the stove, we turn down the greenhouse effect. Okay? We can actually turn down the greenhouse effect significantly by keeping our land cool and covered. Was that a question? No. Okay. But okay, so this is really fundamentally powerful stuff, because see, we've been sort of fixated and told that, hang on, we've got this greenhouse problem, it's stopping emissions of CO2. Okay? And the answer is we've got a much higher agency capacity to keep this thing, reduce the greenhouse effect, obviously through managing the water vapor. We talked about before with hazes, we'll come back into a second, but also to just cooling the planet, cooling the surfaces, stopping that re-radiation. You see? And so we've actually sort of, got to empower ourselves to say we've got to cool this guy. We've been told this is where we've got to go, but yet we can just turn it from high to simmer by turning the landscape into covered, but with a sponge. Okay? And it's just simple physics in that Stoffen-Boltzmann equation, like E equals mc squared. Yeah, you can't escape it, physics. And then you've got to ask yourself, look, there's the Amazon that's still working at this level, right? With soil moisture, transpiration, all that sort of stuff. Hey, and if we concreted the Amazon, would it turn like the Sahara? And of course, that's the modeling says, yeah, it would. The Sahara, 6,000 years ago, was a savanna. What have we done to it? You see? And so, exactly that, all over, basically, as I said, like we talked about Tibet, there's the cedar pollen, in the sediments from 6,000 years ago, it hasn't got the rainfall to support a cedar forest now. Afghanistan, we see the pictures on TV because of all this sort of social trauma, it was like Austria. You know, it was Heidi skipping around with the goats. Okay? So what we've done to landscapes and what we do to climates as a consequence, and in Afghanistan you still see those massive rivers running, you know, all eroding, all sort of, you know, flooding off the landscape, but the amount of rainfall and potential and what it was compared to what it is now, and it's all this effect. Because now Afghanistan, yeah, for most of the time it's a desert, or large parts of it, right? And yet it was like Austria. Okay, so again, agency, our capacity to influence this, but just, I mean, here's the physics, but there's a simple practice, agency, green, longevity, soil carbon sponge, shelter, good land management, right? Now we're going to go back up into the air because we haven't finished all that, but we're going to go into our raindrop stuff, okay? Now, 6. Now we've got this sort of situation. Here's all these humid hazes. And in a sense, they're absorbing water. I mean, they're absorbing heat while they're in the liquid phase. But as they heat up, they'll turn into water vapor. And of course, as they are water vapor molecules, we know these are the principal greenhouse warming effect. Okay, so we've had this sort of, these hazes and the microbial nuclei, the dimethyl sulfate and stuff going up there. It's increasing the haze loads, it's warming in the liquid phase, and it's getting a double whammy warming when that warming from the liquid phase turns it into water vapor, because then it becomes the dominant greenhouse gas. Okay, so this hydrology of the atmosphere, yeah, is a double bang warming liquid and gaseous phase.
Can you explain that? I'm a little bit lost on that one.
Okay.
Double whammy part.
Okay, what we had here when we talked about water vapor, this is actually water vapor as a gas, right? I mean, liquid water doesn't absorb, you know, re-radiated heat, but water vapor molecules do, right? So there's your OH8, that's your little molecule, and it can absorb re-radiated energy very much because basically, okay, I don't want to get into the molecular physics of it, but basically those hydrogen ions, they can absorb heat and just change the bonding shape and stuff a little bit. So it's very, very heat absorptive as a molecule. But this process is in the water vapor phase. That previous process we talked about is incident solar radiation, shortwave solar radiation just heating up the water while it's in the liquid phase. But what we really really sort of trying to sort of make, I suppose, a simple message is that, okay, this water in the atmosphere is very heat absorptive in both phases, right? And we've talked about that we've increased the amount of water in the atmosphere enormously because we put all these additional dust and pollutant nuclei up there, and now we've got these persistent humid hazes way longer than we used to have them, right? And of course then we made the point these persistent humid hazes are also causing aridification because while they're in the haze form, they're not actually forming these raindrops that we need, right? We had that diagram before. So what we've got to do is, how do we get them into rain? But now let's talk about clouds because these are fluffy things that we like really well. Okay, the whole thing, and we said it a little bit before, but now we're going more detail. So the whole idea to turn these haze microdroplets into raindrops, you have to sort of, you have to precipitate about 1 million of them to make a raindrop that's big enough to fall out of the sky. You know, heavy enough under gravity to fall out of the sky. And we need that rain, of course, to restore our sponge. You know, that's really where we're going to get to. And the only way that these haze droplets and the only way rain forms is they have another category of nuclei which are called precipitation nuclei. Okay? And there's 3 types of precipitation nuclei, on this planet. Only 3. And they're ice crystals. And of course we get that when we have a scotch or something like that, and we've got ice in our glass, and the glass is condensing water on the outside, and so the ice is actually hygroscopically, coalescing hazes or water from the air to sort of then condense it onto the glass. So the ice crystal, and of course in high latitudes, high altitudes, and seasonal, storms and winds, these ice crystals are pretty important. The second one that's pretty important here are salts. And of course, most rain over the oceans is precipitated by salt that's come up from sea spray, sodium chloride. And so those clouds are formed by, again, and there's a salt shaker when you're having your fish and chips and you're shaking this thing and it's all gluggy, it won't come out. Because again, it's hygroscopic, it sucks in water vapor, and of course that's the property in the air. Here's a salt particle and it will suck in and form bigger drops. But by far the most important, and especially over land and especially over tropical areas, and it drives the whole Amazon, and coming back to Chris's point, are microbes. Okay, and these are very hygroscopic bacteria. Louis Pasteur sort of basically described them, Aerobacter orogenies, because he was isolating these from the air all the time, but he didn't know what they do. So in Greek, orogeny means I don't bloody well know what they mean, what they're doing there, right? Well, he's a scientist. He has to be honest about how he describes things. But the point is that it's these microbes that are actually by far the most effective at hygroscopically coalescing haze droplets and forming raindrops. And the whole Amazon hydrology is driven by these microbial, nuclei, precipitation nuclei. Now we can go to the biochemistry, microbiology and physics of that at length, but basically what these things, and these are microbes. So then you've got to ask the question, Chris is already asking the question, hang on a minute, if there's microbes, where do they get their food from? Because you can't have microbes without a substrate. And these things are growing in the stomatal cavity of trees. The only place in the universe where there's a free lunch, a free sugar lunch, is where? In the stomatal cavity of trees, because that's where the sugar factory is. Okay? And basically, these things are colonizing, inhibiting, and growing in the stomatal cavity and being transpired up into the clouds as part of that transpiration stream. And so the crystal like this, she's sitting down. So the rain is a microbial symbiotic process in the Amazon.
So why doesn't that exist for, say, grasses in cool season?
Yeah, okay, interesting. A very good question again. So now the question is, does that exist for all vegetation, or why is it only forest? And I don't have a answer for that. I mean, we don't have all this stuff, we don't have all the answers. It's science, right? But we do know that, for example, you guys, Christopher Columbus, 1492, sailed from Portugal and basically came to America, right? On his way back, he stopped at Madeira, which is a little island off Portugal. The Portuguese had found that in about 1410. It was rainforest. It was mahogany rainforest. Okay, you got it. It was and they basically, and it's all documented, the Portuguese were very, very good documentation people in terms of their colonial management. They cut 2-meter diameter mahogany logs, floated them down on the rivers, cut them up with water-powered sawmills, and that's what the Portuguese built their caravels out of. And all the caravels, they went into the East Indies. How much mahogany grows in Portugal? Zilch. None, right? So that's how they grew their ships. Well, if you go to Madeira now, it's cactus. It's basically like the Canary Islands, semi-arid shrubs, cacti thing. No rivers, etc. So what we're saying is, why doesn't it, or where does these nuclei get produced? And we know that if we destroy the forest, right, we destroy the rainfall. Okay, because Madeira is a case study. Conversely, there's another island about sort of 1,000 kilometres south of Madeira called Ascension Island. Okay, and the British used that for a long, long time as a naval resupply. They put goats out there. The goats desertified the whole place. And then Charles Darwin and Hooker, in about 1875, sort of said, hey, this is, we're degrading this. Can we regenerate it? And they started replanting and, excluding the goats. And now Ascension Island has got forests, one of its mountains, not all of its mountain. One of the mountains got Green Mountain, it's called. And basically it's restored its rainfall. Okay, so we've got, okay, and there's lots more of that sort of evidence we've got to bring into it. But no, why does not all vegetation produce these? And why only, particularly mature forests? There's more evidence, but we won't go into it now, physiological evidence why it could be. The point though here is that, look, to get this humid haze out of the air into raindrops, you need precipitation nuclei. Precipitation can't occur without these precipitation nuclei. And really, there's three categories. And obviously over land, it's these, forest-driven bacterial precipitation nuclei. Glenn, you were saying? No, okay.
There's questions over here.
Oh, sorry, yeah.
Is that why they talk about seeding the haze?
Yes, yeah. Okay, very good. Spot on, exactly, thank you. Because basically, when you Schaefer in America in the 1940s basically was doing the work, we got onto it then with our atmospheric physics, CSIRO, where I was working, in the 50s and 60s. The Israelis and the Chinese and others are still doing it, because that's what we do, cloud seeding, right? And what we use is silver iodide, and it's sort of, again, better than sodium chloride, and it's used as a salt, and we can fly into clouds, we can aerosol this silver iodide vapor, and then it will seed clouds because it's acting as a precipitation nuclei, right? And we did a lot of experiments with bacteria and CSIRO, and by far they were the most effective hygroscopically at coalescing in cloud chambers. But there's no way we can disperse these things, because when you grow bacteria, they're like glug, right? And so how do you atomize these bacteria to disperse them into cloud? And we didn't have the technology for that.
It's called a tree, right?
Well, okay, yeah, see, and those experiments, and as in Ascension Island, those reverse experiments, Ascension Island shows that, yeah.
So someone said mature tree, is it a particular
Okay, okay, look.
of a forest or?
Okay, and I mean, absolutely honestly, this is, okay, Louis Pasteur did this initial work. He identified these bacteria. He didn't know what they did or why they were. He's just amazed, how come there's all these bacteria there? He climbed to the top of Mount Block, took air samples. He went up in balloons, not he, but others went up in balloons, took air samples from 20,000 feet and stuff. These bacteria, that you've got to... He wrote a textbook in the 1880s called Aerobiologie, the aerobiology, right? But it was really describing what we knew, but there's a lot we don't know. And so, yeah, with its mature tree, what species of tree, what density of forest, in what habitat, we don't have all those answers, but we do have a lot of information. We know that, yeah, this forest is driving 80% of its rainfall through this process, like the Amazon and stuff like that. In the Amazon, we've done labeled studies with tritium, and we can actually establish how much of the water cycle is driven through these microbial vis-a-vis just transpiration, and over half of it is driven by these microbial processes. Well, yeah, but I mean, okay, but we're just looking at tritium, and so that's all we can, that's what we can confirm. But
I
plus,
think in the Amazon, I'm not sure, I haven't really researched it, but I think that there are certain key species that if
Yeah.
you remove them,
Yes.
the whole system falls apart.
Yes.
Whether that's because
Yeah.
you don't have this
yes,
output or not.
no,
Species or microbial species?
No, tree
tree species, yeah. Because again, if you grow a plantation, you don't get the same effect, right?
So it's possible that you would have, I mean, I can't believe that you don't have these bacteria. I've seen them in stomata in other plants, but it may be the particular types of trees that help to add for the dispersal mechanism. Because the way that the bacteria that you're talking about, you can't atomize them because to protect themselves from solar radiation, the bacterial cell walls, and to be hygroscopic, they're going to have a little bit of a different cell wall composition that you couldn't, that is going to cause them to clump in most conditions.
Yeah.
So it may very well be something that they're getting from these particular, so you'd get the same type of bacteria on other plant material, but their ability to basically be atomized and dispersed may be sort of partially regulated by something that they get from, in some way, some kind of composition component with the sugars that are created.
Yeah.
Maybe the height of the tree too.
Yeah.
The height of the plant.
The height could make a
Yeah,
difference, but you'd
yeah.
also, you'd
Yeah.
also certainly want
Yeah.
a mechanism
Yeah.
there.
We have a lot of, I mean, okay, so I've spent, 6 years researching, like forensically collecting the data that gives me the picture, the map, the pattern analysis. And look, actually, we know a lot about the whole biochemistry of these things and how they work. And it's fascinating, really fascinating. For example, the bacteria go up, and as you say, they get zapped by ultraviolet, so they don't come back as living bacteria. But they produce, they convert sugar into particular glycol molecules that are extremally hygroscopic, some of the highest water activity of any substances we know, and it's the actual, the hygroscopic carbon substances they produced that are the things that are, absorbing these molecules, not the living bacteria. Okay, and so then they come down with that. The other thing that's interesting, and we raise that, like here are the bacteria and they're colonizing these stomatal cavities, but that's because there's free sugar there. But what's stopping all these other saprophytes and opportunists coming in then and clogging up all the stomata? And again, we've done all this study. I didn't do it, this is previous work. And these things are producing what we call, again, crystalline, phytolexins, and they're basically inducing an immunity in that canopy, okay, which then they can tolerate, like it's an antibiotic, so they're in their canopy, that they can tolerate, but other bacteria can't. And so here's again a symbiosis in the canopy of these trees that is optimizing their transpiration, their rainfall induction, but it's a very beautiful, elegant microbial symbiosis, tree, bacteria, running that whole hydrology. And we've got other organisms like Pseudomonas syringae and stuff like that live on the outside of leaves, and they sometimes have some of this effect, but nothing like the same dominant role. So there's a lot of, lot of background information here, and we're getting a very good picture, but the critical question, what tree, what height, what species, what density, how old, no, we haven't got those grassroots studies yet.
So there's some books written about electromagnetic fields causing rain. And I have, based on that, done virtual copper lines, which I've seen every single time cause rain.
Okay.
So where does that fit in?
No, okay, well, look, let's explain. These aerosols, these haze droplets, are often charged. And because they're charged, they're dispersed, but they can't coalesce by themselves because they're all repelling each other, right? And so what's the whole hygroscopic nature is here is a biochemical hygroscopicity that overrides these charge repulsion things. And certainly the Russians did a lot of work to say, yeah, if I can come in here with positive charges, sort of anodes with positive charges, cathodes with positive, then basically can I coalesce them? And technically you can, right? But then the logistics of how much, how much electricity I put up there, and certainly it's part of that whole coalescence process, and certainly the hygroscopicity is really overriding those repulsion charges. Yeah. Okay, so basically we've got, coming back to Chris's issue, you see, so now we've got a microbiology that's basically driving the rainfall. It's driving both the creation of the hazes and the removal of the hazes as rain. And so now this gets pretty spooky, you see, because now we're talking about how much of that hydrological dynamics is governed by the biology, of life on land.
I'm sorry, Walter, how is the microbiology affecting the creation of the hazes?
Oh, okay, because we've got, good point. Here is the dimethyl sulfide and the terpenes. Okay, and these are coming from trees. This is a Jefferson sort of thing. This is from the algae in the ocean. So all of these are small carbon volatile compounds, molecular weight just over 100. Okay, so there might be 4 to 8 carbon chain, little volatile molecules. And basically these are all produced by microbiology and, in this case, plants, But it's biology producing the haze nuclei, and here we are, biology producing the precipitation nuclei. And so now the question is, how much does Mother Nature regulate the warming hazes and then the removal of these things through these microbial processes? Actually, I must add, see, we got sidetracked, Paula. We got sidetracked. As these, and this is, you see, I apologize, As these things go into raindrops, before they go into raindrops, they of course produce these things called clouds, right? What an omission. I forgot the clouds. Okay, so as these hazes get coalesced through these nuclei, they'll produce clouds. And these are dense, high albedo clouds. These are hazes, okay, but these are now these dense, high albedo clouds. And these high albedo clouds, of course, are super effective at reflecting solar energy back out to space. In fact, on average, 50% of the Earth, how did I forget this, Paula? 50% of the Earth is covered by clouds at any time, and they reflect 120 to 130 watts per square meter of that 342 back out to space before it even gets to the Earth. Okay? So this is again a heat buffering mechanism. Okay? Now, what it's saying is that these microbial processes in turning these hazes, warming hazes, into these cooling clouds and then raindrops have a profound heat effect. But I should be whipped, shouldn't I, for forgetting my clouds? We got lost into nuclei, you see. But no, okay, so do you get what I'm saying? So again, the planet, Mother Nature, runs this system, through removing these hazes, making these clouds, and immediately going from a warming dynamic to a cooling dynamic. The rain itself, removes those clouds in, and we start all over again. The rain, of course, goes down here to make sponge. Okay? So basically, no. We've got to hang on. Yeah. We've got to have carbon. Hang on. No. We know Peter's down there making carbon.
The rain stops coalesce, also releasing more heat.
No, basically as these clouds form and they're coalescing hazes and water vapor into the clouds, they're releasing massive amount of heat, and that's of course what that whole thunder, that's the whole cloud dynamics and then thunderstorms. It's this massive release of latent heat of vaporization from not so much the haze droplets, but the water vapor that it's coalescing and condensing at the same time, right? Yeah, so we'll just think. Okay, so what we're really getting here is, like India, desertification and what have you, this is really fundamental. It's basically like, okay, we've got to rehydrate this planet, we've got to cool this planet, we can only cool the planet through these natural cycles, and we've really been making the message that, okay, the biology of how we manage our land system has a profound effect on these dynamics. And of course, the powerful thing there is agency, because we are the ones that very much manage that land surface. So the idea that our actions on the land can directly influence the climate, whether it's hazes, whether it's albedos, whether it's transpiration, whether it's cloud formation, whether it's rain formation, gives us an enormous, positive. Yeah, that's what Mother Nature did, and we're not saying we know everything about every part of it, but all we're doing is, can we regenerate these natural biosystems to build that sort of back?
What the most miraculous thing about this is, climate scientists don't understand any of it.
Okay, yeah, Abaddon, you're right. Actually,
And some of them do.
No. Okay, no, I agree. Okay, but if you go to any climatology 101 textbook, this is in a sense the start. Here is the heat dynamics of the blue planet, and they'll have all these different processes drawn in there, and here's energy coming in, energy going out in different processes. They haven't actually explained, they don't explain the mechanisms as we've gone through, but basically it's climatology 101. But you're right that our greenhouse climate politics has completely ignored all of this. Okay, so I just wanted to, we'll have a bit of a break. There's several other processes that follow this, which give you additional cooling and rehydration. But in a sense, this is now the core, the guts of, the mechanisms that we influence. There's some positive dividends, and, how do we actually, forget about India, how do we turn California back into what it could be and should be and has to be if you're going to keep America together? Okay, I've seen some data, rainfall data, Whitney was a guy, he did a PhD and wrote From Coastal Wilderness to Fruited Plain. It was a book he wrote, right, back in 70s, right? It was his whole thesis. But he's got some really good data. But there's also another study which is really stunning, and it's part of the background I've got, where because you've got deciduous trees, they've basically mapped the formation of cloud and rainfall with the actual, in springtime, the actual leaves of the deciduous trees coming out. Okay, so down in Florida, Carolinas, and Washington, and as you go up the East Coast, the deciduous trees shoot at slightly different times. There's about 3-4 weeks, as they go further north, and then they map the actual formation of cloud and rain with the opening of those deciduous trees.
So that's the spring rainfall.
Yeah, that's the spring rainfall coming with that sort of opening of those trees. And of course, I'm sort of saying, hang on, what is the agent? Nucleation, etc. Now, it's not proof, but actually the association was stunning and completely significant vis-a-vis all the other factors, right? We've got another one in Western Australia. So we've got the Indian Ocean, and then we've got Western Australia, and the rainfall obviously then dropped down from the coast, and it got drier and drier inland. So naturally, this was sort of like 6 inches, and it was like 14 inches out here in nature. And of course, what we did, because we're Europeans, we then basically said, look, we can clear all this good country with enough rainfall to grow wheat. Okay, so we bulldozed all the vegetation on this country because, yeah, that was 14 inches and this sort of ended up at 10 inches, and then we thought, oh, well, bugger that, that's, getting too dry. And now, and then, okay, we put a fence in, we call it the rabbit-proof fence, right? And there's a film they made about this with Aborigines and stuff. But now we've got this interesting thing, you see, because if you look at the rainfall across there now, it goes like this. And these get now 20%, these guys 20% more rain consistently than on this side, yet that rain has to come from the Indian Ocean across the dry, cleared wheatlands, and basically on the rabbit-proof fence. And of course the scientific hypothesis is, does barbed wire induce rainfall? I mean, you can get a research grant on that, come on. Don't knock back a research grant, right? Susan, you wouldn't knock back a research grant, would you? Okay, but the point is that, no, 20% consistent, reliable difference now in the forest vis-a-vis where the wheat country is. And of course everyone's complaining we were robbed, we should have cleared that country.
Is there any guess of how small a swath of trees can produce rain?
Okay, okay, look, I mean, thank you very, very much. And these are like, okay, we talked about Madeira, and Madeira is an island about 40 kilometers by 10 kilometers, right? But there's a friend, Willie Smits, in Kalimantan in Borneo. And he was rescuing baby orangutans because they were decimating all that forest. All these orangutans were getting sold as pet food or bush meat in the market. And he was rescuing them. And so he said, look, I've got to build a refuge for my orangutans. And he bought 5,000 hectares of land. That's about 12,500 acres. And he then started regrowing a rainforest. It's been growing for about 15 years. And again, he's getting a 25% increase in and downwind of that rainforest. Okay, and that's, so I mean, obviously that condition, and it's tropical Kalimantan, but basically, yeah, that sort of scale of reforestation in that sort of environment, in that sort of time, yeah, it's doable.
20 square miles.
Yeah.
One that I know about is only 17 acres.
17 acres, okay, yeah, see. And I imagine, okay, well, we should talk, oh, well, no, we've got a break. But the point is that, we'll come back to California later on, we'll talk about water harvesting. And yeah, it might just be a row of sequoias on a ridge, as simple as that. Okay.
All right, so we're gonna, yeah.
Hey. You got to ask, I mean, you've got to answer all the hard questions later, so don't clap till you can answer them.
Well, just enjoy it while it lasts.
Yeah, okay. Okay, fantastic. Look, just recapturing, and apologies, you see, there's somebody pulled me up, that a raindrop isn't shaped like that at all. You know that, don't you? Raindrops come down in little donut type of things, right? And so for those... No, this is important. Like we're talking about rain. It's important. Anyway, yeah, no, look, we've worked, I mean, they've worked out the raindrops actually fall as donuts, and then, of course, they impact and penetrate. So there's a whole lot of physics behind that. The other thing is that people got a bit confused because in terms of numbering, and I'm going from one process, like here's Stefan Boltzmann, and that's the amount of re-radiation, and then I go into the next step and say, okay, here's the greenhouse, how do we turn it down? So whether that's one number or if it's two numbers, so what we're really doing, we're paddling down the river, right? We're going on a cruise, a journey through what nature does with hydrology, and there's steps along the way. I've tried to break it up, and this is actually very, very important, you see, because nature doesn't break it up. It's all one matrix of symbioses, of processes, and nature just then says, okay, well, what do I need where? And she just takes what she wants from whatever the process. You see, so it's not linear as I've been describing. It's just that we have to start and we do have to finish. And so it's this matrix of processes, this toolbox, these processes, and then she can take whatever she wants when she needs it to do whatever she wants. So it's very sophisticated. What I wanted to do now, though, is I just wanted to, okay, we've got basically rainfall, we've got clouds, And it doesn't stop there. I mean, but there's a few key ones that I think we should just go on with to try and complete our paddle down the creek or the river or beautiful lake, and just get some perspective on the, other hydrological cooling options. The other one that we want to talk to now is about the thing called radiation windows. And this is actually pretty important, particularly in urban areas or built-up areas, right? It's quite significant that 60% of the warming, global warming that we're recording and experience is happening through increased nighttime minimum temperatures. Okay, it's the nighttime minima that are becoming warmer or not as cold. And of course, CO2 doesn't vary from daytime to nighttime. It's the same. It's going to be there for hundreds of years. And so, of course, it can't explain, why 60% of the warming effect is through these higher nighttime minimum. But in a sense, what happens when you condense the water vapor out of the sky through these rains, right? Then you take a significant part of that greenhouse effect away, because you've taken all that haze, you've taken all that water vapor molecule and the clouds, and you've removed them. And of course, especially in tropical areas, you've got this very clear seasonal pattern, diurnal pattern. So this is time of day, and this is sort of rain, and of course you basically have pretty clear skies, you build up clouds. Then in tropical areas at 4:45 p.m., you basically have a thunderstorm. You set your watch by it because, in Malaysia and Kalimantan and stuff, exactly that. And so it's a sense, all this transpiration happening. Okay, you've got this massive nucleation event, you have that thunderstorm, and you end up then sort of having actually it doesn't build up quite that fast, but then you have a build up again, from middle of the night sort of thing. But you have this gap here, and you remember all the Somerset Morn and all the romantic novels from the tropics, and then, the starlight night after the thunderstorm. And you have a radiation window, because having removed the water vapor, so this is high water vapor, but then you've had that reduced water vapor, and at this stage you can get a lot of infrared re-radiating back from the heat, back from the surface out to space very directly. And so this is a radiation window. CO2 stays the same right throughout the thing, but there you've got this radiation window. If you don't have this nucleation, if you don't have that rain, because you don't have the precipitation nuclei, actually it gets really serious, because you stay muggy all night long, and of course you have a very uncomfortable night, and you don't have this cooling. Now again, this radiation window varies different parts of the world, but yeah, it can be 30 to 50 watts per square meter. So again, we're making the point that, again, here's another tool, another process that nature uses, okay, to actually help cool the planet. And in different regions, certainly in the tropics, these are critically important. And if you don't have these thunderstorms, then you end up with this very oppressive problem of, 95% humidity staying. And why it's important is, you probably would have heard about that. In the Persian Gulf, for example, now, Kuwait and stuff, there's so much dust, there's so many haze, there's no rain, of course, and they're getting to situations in their summer where they're getting 90% humidities, temperatures of 50 degrees, and it's getting to the point, if we get temperatures, at that level, without the capacity to cool ourselves because of that very, very high humidity, then Homo sapien, just doesn't have the chance to survive, right? With 37.8, 30, what's our temperature? 7.8, yeah.
Celsius.
98 Fahrenheit. But the point is that that's our temperature, and above that, we have to sweat to regulate. And we cannot, fever, if we go 3 degrees over, we're cooking, right? We're very seriously and risk then dying. And so this is the point, and we're talking about this in terms of dangerous climate extremes, because in large parts of the world, in those Persian Gulf, in those Middle Eastern areas, we are now at the threshold where it's getting terminal for human survival in those summer months. Because the humidity's that high, the temperature's that high, they've aridified the whole landscape, and it's becoming close to uninhabitable.
Maybe you've already gone over this, but why isn't there that radiation window in the Middle East?
Oh, okay, so, right, okay, well, yeah, we have, but I mean, yeah, look, what it is basically there's water vapor and transpiration and humid air inflow, but we need the rain to happen to clear that water, and that can only happen when it has precipitation nuclei, when there are nuclei in that air that can coalesce these hazes, coalesce as water vapor, and drop it out as these donuts. Not raindrops, as we've seen, donuts.
And what are the nuclei? Like how?
Okay, no, good. We've talked about that, but no, that's important, because the 3 types of nuclei exist, that's it, precipitation nuclei. There are ice crystals, which happen in high altitudes, high latitudes, and for some of our frontal rain, right? And you know that like here's ice sort of coalescing humidity. There's salts, sea salt. When you try to shake your salt on your fish and chips, you can't get it out of the shaker because it's all gone gluggy, hygroscopic. But the most important thing, the most important nuclei actually bacteria, microbial nuclei produced by forests, and this is how nature actually regulated much of this whole hydrological cycle. Obviously, again, in those regions, they don't have any forests left. It's all just desert, and they're just in this. And then they've got lots of pollutant, hazes and stuff like that, especially when Saddam was burning all these oil fields. And it just got, it's just a toxic, hot, humid soup. Okay, so here's another cooling option. Sorry?
No,
Sure.
well, when they grounded all the airplanes,
Yeah.
because of the World Trade Tower.
Yeah, no, exactly. Good, beautiful.
The change between daytime and nighttime went back to old time.
Yeah,
In other
yeah,
words,
yeah,
just
yeah.
in that next 2 days, there was a big drop.
Thank you very much. Yeah. And that's exactly that. That's that humid haze that we talked about in the beginning. High altitude humid haze. And obviously as these aeroplanes fly, they're burning kerosene basically. There's a lot of carbon particulates that come out obviously as exhaust, and they are all acting as haze nuclei, right? And in a sense, exactly that. You had clearer skies, and you then basically went back to, 2 days of planes out of the air, and you went back to normal conditions. And again, it's one of these, the evidence is everywhere. I mean, there's that sort of beautiful evidence, but I mean, you can't put numbers on it exactly, but yeah, the effect is profound. Yeah. Yeah.
Repeat the experiment.
Yeah, and well, we're going to get to that stage if we don't watch out.
Quickly things can recover.
Right. Now, the other thing that I wanted to talk about, I forget what number we're up now, but the other thing we want to talk about, and this is now on the global dynamic scale, and it's called the biotic pump, and you probably know a bit about it. But basically, when you get rain, okay, and you've taken all this water vapor out of the atmosphere, and that hot water vapor was, like molecules that were sort of vibrating, and that vibration and that heat creates pressure, because that's what pressure is, heat and stuff. And so basically, when it rains, you actually go into a low pressure sort of atmospheric thing. This is a high pressure environment, right? And then you go into a low pressure environment. And so on a continental basis, and now let's just say draw Latin America, okay, something like that. And basically, you see, you have rain over the Amazon, and that creates low pressure, and that allows more high pressure humid air from the Atlantic Ocean to flow in. And so you end up with this biotic pump. The rain itself is creating lower pressure, higher pressure humid air from the oceans flows in. It again precipitates. And so basically the rain goes all the way to the Andes, and basically you've got all this influx of humid air across the continent, of course, keep rehydrating or hydrating the whole Amazon and keeping that whole thing working. In fact, this is a cycle, and basically each molecule of air, water vapor, cycles about 7 times diurnally as it moves across the Amazon, right? So the same one molecule of water will go through this, transpiration, precipitation cycle, each time cooling, the planet as it moves along. But this is, in a sense, a biotic pump, and so this is fundamental because that is, in a sense, what hydrates, regions, continents, California, right? And so it's these sorts of things that actually are fundamental in keeping regions rehydrated. Conversely, if we clear the vegetation, if we prevent this sort of rain formation, we're heating up the land, as we saw before. We're going to, higher temperatures, higher re-radiation, building high-pressure domes, and you end up with, in a sense, heating the land, and you create a high-pressure dome over that area, and of course that then excludes any humid inflow. You don't get, from relatively lower inflow into these high-pressure heat domes. And so the Sahara is obviously a high-pressure heat dome, and that's, in a sense, preventing rain coming in, even through the Sahara and what have you. And so this dynamic that we're talking about, like all these hydrological dams, have actually continental significances. And so from an Australian point of view, again, we've got a little continent here. Well, how do we draw it? That's the thing. Bit rough. There's an island down there. That's Tasmania. But basically, we've got this area here called the Indian Ocean. And the Indian Ocean is the world's most intense evaporation basin because the way it's on the equator, but also it's the way it's structured with little inflow. And so we get massive evaporation. Of course, that drives the Indian monsoon, the whole Asian monsoon. But on the other season, it used to drive the Australian monsoon. And so we have basically humid air flowing across Australia in our summer. And there's 10 times more humidity that flows across this continent than actually sort of falls as rainfall. You see? And so one of our challenges is, how do we actually look at revegetating, rebuilding, some of this process that we've been talking about, and can we restore the Australian monsoon? Now, no one's promising that tomorrow. Build a barbed wire fence. Yeah. Well, actually, no, you're right, because see, the barbed wire fence is about there, and exactly that. Yeah. No. There's smarter people. way beyond my pay grade. Build a fence. Yeah, why not? But anyway, the score is, you see, quite seriously, here's the Australian monsoon. Yeah, can we restore it? What have we done to destroy it by our burning of that continent for the last 40,000 years through, indigenous land management? Because if you go back in paleohistory again, then basically Lake Eyre, which is now in the middle here, it's a 4-inch rainfall desert. That was, in a sense, a 25-meter deep freshwater lake. We still see the freshwater mussels in the sand dunes around the lake. And you see, the point is that we did have an Australian monsoon. We go back and do the pollen analysis again, and there was Calitras, casuarina, all these fire-sensitive sort of subtropical savanna species, and it was a different world. Okay, so what we're trying to raise the question here is that, this is at the micro level, and we've been talking about, nuclei at the microscopic level, but it also comes to the continental scale. And so she's beautiful, isn't she? Mother Nature, she sort of basically says, look, I can use these processes and bang, I can, run a monsoon, I can regreen a continent. So that's actually the thing. Now, what we've been talking about, and at the beginning when we started this morning, was a case of, we've gone through that lot. Oh yeah, sorry, Adam. Peter, sorry.
It might help people to understand the biotic pump a little bit better if you basically take the condensation of water vapor as a gas, it takes up a lot of room.
Yeah.
Remember the gas laws. When it condenses into liquid, it's a tiny, tiny fraction of that volume. And that's what lowers the pressure when water condenses into raindrops. That lowers the pressure, and that is what pulls the maritime air into the continent.
It creates a lower pressure, like a vacuum, and then you get them out of the air effectively flowing in. Right?
And is there also the fact that the heat rising above the land is, since it's rising, that it's pushing?
Yeah, okay, well, yes, and yes, and of course there's a big global heat pump, the Hadley cells, which are then, as the planet is warming, the sort of the latitude 20 north, 20 south is really heating up the most. That's increasing more hot air, more high pressure, and those pressure belts are pushing out. Okay, let's look at, draw your California. Okay, there's Alaska, and then California, Bay, and I'm not good at this one, see, okay, and there's Hudson Bay, and then here's New England, okay, and here's Vermont. Okay, look, I know the Gulf of Mexico there, yeah. Anyway, the point is, you see, so, no, but they're like coming just exactly what, and here's the... Very bacterial. Very bacterial. And basically, but what's happening is, these high pressure zones, okay, this is wet equatorial, but then above that, and then these have been expanding, and they've been expanding about 300 kilometers, both north and south. And these are we call the Hadley cells, right? And this is sort of like heating in the central equatorial area. It's heating up because it's getting hotter, the high pressure areas expanding north, right? So the heat air rises and then descends, and you get then hot, dry air, and that's further north. And so what was happening back here in Mexico is now very much moving up into California. And so California here is sort of starting to aridify systemically, so that's aridity, and quite frankly, it's there to stay, right? I mean, you've got these pressure influences, but you still have these humid, moist airflows from the sea, and now the question is really, are you able to capture and precipitate and all what we've been talking about in terms of, heat pumps and condensation? Are you able to do that?
Well, I thought the poles were heating up fastest.
Yes, certainly you're right. The poles are certainly heating up fastest, but basically, as a temperature increase, but most of the heat is still going into the equator, right? I mean, actually, on another measure there, most of the heat is actually going into the oceans. 93% of the excess heat that we're getting is actually warming the oceans. So we're not actually seeing it. And this is compounding that whole question. We've got things are cooking, Charlie, and they're going to come and hit us hard. And because, the oceans are heating, and as we said, as the oceans are heating, they're going to give off more CO2. And so that's why, the CO2 graph is going to keep on going up no matter what we do regarding fossil fuels.
Can I just one other thing too, is that we're talking about radiation windows and biotic pump and the rainfall and cycling of rainfall, as you mentioned, you can get 10 times as much, 10 cycles out of a...
Each model going on.
And that cycling means that you are evaporating each time.
Each time cooling. Yes.
Cooling that you would get if you just lighted once. So that cycle, if you cycle every day, as in a rainforest, you can get an enormous amount of cooling. If we destroy that biotic pump, which kind of makes that happen by deforestation, basically, then we don't have nearly as much cooling from that effect. And so each time it rains, that's telling you that if one large rainfall, it may not be as effective as multiple rainfalls.
Thank you very much, Glenn. And look, this is so important because remember we talked about the longevity of green, and the same thing, how many of these cooling cycles, the one molecule of water can give you 10 times the bang for the buck, because if it's, as Glenn just said, cycling, and every time it goes up, it's taking 596 calories of heat, taking it up into the atmosphere, pushing a lot of it out to space, coming down as rain, and off it does it again, right? So that speed of cycling, of course, the punchline Glenn didn't talk about, it all depends on your sponge, right? Because if you don't have the sponge, you don't have the water, hey, you don't do the cycling, right? And so that's the thing. If we're growing this stuff on concrete, no water retention, hey, and we get a storm event, but that's it. We've got to wait another 3 months before there's another storm before we have some water. Whereas if we're the sponge, we can do this every day.
So I'm stuck back a minute where you talked about a high pressure zone.
Yeah.
And then raining, and then it goes to a low pressure zone.
It's what Peter sort of said, you know, as it rains, that water that was there in water vapor and cloud droplets all is collapsed into that rain droplet. You know, a million of these things come into a rain droplet. That rain droplet falls out, and so effectively all that heat, all that water vapor is now removed from that void, and so it has now low pressure, and it allows other humid air to flow into it, which is higher than it is, right?
What?
It's like creating a suction.
No, so that was the beginning of what I was understanding.
Yeah.
And then you were talking about the Sahara,
Yeah.
where it's a high pressure and it prevents.
Okay, okay.
So that's what I'm not understanding.
No. Okay, so it's relative, right? I mean, so the lowest pressure is when it's just rained. Here's that humid air, which is higher pressure than where it's rained. But the Sahara heated, hot, dusty air is, 20 times higher than the you know, like it's so much higher, right? So,
Okay.
So you're looking like, okay, here's, how do we do a graph? Okay, here's the Sahara, here's the saturated air, and here's the non-saturated air, right? Okay. And so relative, I mean, that's pressure, and that's the sort of state. So what I'm saying is it's relative to that, and so you'll get air flowing. Okay, once you take it down there, you'll get more humid air flowing in there, but there's no way any of this air here can flow and displace that stuff. It just excludes it.
Keep in mind that water vapor weighs less, has lower density than air, so it tends to rise, but it also, that means that it's greater volume as well for the same mass of you know, the molecules.
Yeah.
So
Okay.
you're saying that high pressure is like this huge wall.
Yeah, it's like a huge mountain that you would have to climb to try and get over, and you can't, you know. But it is a significantly higher pressure there than this, okay. And it's always relative A to B, right? But, okay, so let's go back to the beginning. We started off with saying, look, why climate change, or why we've got this issue, and really the criticality of the next 10 years, because if we don't do that, we've got, you know, this dangerous climate extremes, Irene, Sandy, Katrina, bushfires, you know, aridification of California. We then sort of basically say, right, what are we going to do about it? We came to the conclusion that no, we can't just fix it by carbon drawdown or stopping fossil fuel because of the ocean lag effects, etc. We actually have to safely, naturally cool this planet. And so for the last sort of 2 hours or more, actually, we've been talking about, okay, what are the options? How did nature cool the planet? What are this sequence of processes? And we looked at the science, and actually we brought in the discussion, which is good, we brought in some of the practicalities. Now the practicalities come to the examples, whether it's Kalimantan or, you know, as we've been talking about, examples of where, you know, these sorts of things are operating. And I suppose the next step is, well, what are we going to do about it? What's the actual agency or the action? And in a sense, this is what you guys in America are going to face in the next, you can't escape it, in the next 18 months, right? You've got to decide, what are you going to do about California? You know, as we've described here, you see, you've got a situation, the snowpack's gone, you might get summer back occasionally, but it'll be progressively less every year. You've basically grown all that agriculture in the San Joaquin Valley on groundwater that you've been pumping. It's 80% plus, you know, drained now. And you've got this whole bushfire scenario, which is every 2 years burning the guts out of the country and progressively aridifying it further and further. And
when you say we've got to decide what we're going to do with California.
Yeah.
I don't see that we have much of a decision
Yeah, okay, that's what,
to
okay.
make.
Good, because I want to foster this debate, because now we're talking about not the science, not the practice, but the politics, right?
That's right.
Yeah, sociological politics.